Hi, my name is Melissa Micah. I'm with the Hydrologic Engineering Center. Welcome to Regional Precipitation Frequency Analysis. This video is part 4, Framework for Regional Frequency Analysis. When performing streamflow frequency analysis, we typically turn to Bulletin 17C. We don't really have an equivalent for that for regional frequency analysis like precipitation frequency analysis. This book by Hosking and Wallace, published in 1997, is the holy grail of regional frequency analysis and is based on an approach using L moments, or linear moments, that we discussed in part 2. Much of the techniques in this book have been implemented in various R packages like LMOM and LMOM RFA that make the process much easier. The LMOM and LMOM RFA packages also have example data, and it's really useful to go through those examples in R to help learn the concepts. This is a basic summary of the steps outlined in Hosking and Wallace for regional frequency analysis. The first step is to collect data, then we form homogeneous regions, compute L-moment ratios, identify the probability distribution, and estimate the parameters. I'm not going to talk too much about the first step of collecting data in this video, but keep in mind it's still important to produce samples that are IID, or independent and identically distributed, as we talked about in some of the other lectures. For precipitation data, we typically work with annual maximum series. Some of the common data sources are for daily precipitation data such as GHCN, or NOAA Atlas 14 publishes the annual maximum series that were collected for the various volumes. If you do collect your own data, make sure to perform quality control, especially when using precipitation, which is prone to error. The next step that we're going to talk about is the creation of homogeneous regions. This is the so-called first law of geography by Waldo Tobler, which says everything is related to everything else, but near things are more related than distant things. This might seem intuitive, but is actually very foundational to concepts of spatial dependence and interpolation. This step in regional frequency analysis is to create physical regions. The goal is to partition sites into homogeneous regions. There's some R packages to help with this, such as R-cluster. In the figure to the left, we see a bunch of gauges in the Pacific Northwest, and the goal is to collect those gauges into regions that are reasonably similar to each other. If you remember from one of the earlier videos, sites located in a homogeneous region should have very similar L-moment ratios. We typically use spatial variables to define regions. A good place to start is climate divisions, which is shown in the figure to the left. These are produced by the National Weather Service and represent areas that are meteorologically similar. Once you've created a rough idea of how the regions should be defined, you can further refine them using other spatial variables. Location, like latitude and longitude or planar coordinates, are another good place to start. As we saw in Tobler's first law of geography, near things tend to be more similar than far things. Other variables such as elevation, climatology, like mean annual precipitation or temperature, proximity to coasts, mountains, or other features also tend to be helpful variables to create physical homogeneous regions. Here's a quote from Hosking and Wallace, which is the book on regional frequency analysis. They state, "Of all the stages in a regional frequency analysis involving many sites, the identification of homogeneous regions is usually the most difficult and requires the greatest amount of subjective judgment." Keep this in mind when you're performing this step of regional frequency analysis. Developing homogeneous regions is probably the hardest part of the analysis and requires the most subjective engineering input. Here's an example of sites in the eastern US, in Georgia, South Carolina, and North Carolina, that are colored based on their homogeneous region that they're assigned to. As you can see in the circled area, the regions are not spatially contiguous. They're overlapping slightly. This tends to be more common in areas with large differences in elevation or other defining features. If we hone in on this same area on a topographic map, you can see that this area corresponds to areas of high elevation along the southern Appalachian Range. When performing regionalization using some of the methods we talked about earlier, like index flood, it's very important to have continuous regions, such as this section of the map here, because you have to assign a site to a specific region. For other regionalization methods like mapping, we're able to overcome this, where we don't have to have continuous regions. The other point here is that these regions tap into the key properties of the extreme rainfall in the area. which spatial proximity alone can't describe. Once we've taken all of our sites and assigned them to regions, we have to perform statistical tests to ensure whether those regions are homogeneous or not. In the next couple slides, we'll talk about the specific tests we can run to check for homogeneity. When considering a region, there's a continuum of relatedness. Regions that are too large or too uncorrelated may no longer be considered homogeneous. Regions that are too small or too correlated may not be independent, which breaks our assumptions of IID in our data. So on one end of the spectrum, we have events that are perfectly uncorrelated, which means that all observations are completely independent, which means that they might be heterogeneous. On the other end of the spectrum, we have events that are perfectly correlated, which means there are no independent observations, which means it is homogeneous, but it's not adding any information to our study. Imagine we have two precipitation gauges located mere inches from each other. They will probably measure the exact same storm events for the entire period of record. Combining the information from these two gauges together doesn't actually provide us any new information. And so that's where this balance comes in. We aim to have regions that are mildly correlated, so that the regions have many independent observations, but are still probably homogeneous and represent the same phenomena. So that's the sweet spot here that we're aiming for when we're producing these regions. This means that event occurrences typically affect more than one gauge at a time, but each year the sites collectively observe several different events and capture the variability. Now we'll talk about the statistical tests that you can run to test whether a region is acceptably homogeneous. The goal is to check whether the variation in the L-moment ratios in the region are more than expected. We expect some variation to come from sample error, but we do expect that a homogeneous region should have similar L-moment ratios for each of the sites in the region. If the variation is too high, the goal is to circle back and reformulate the regions. The first test we'll talk about is called the H statistic, which is a homogeneity metric. If H is less than 1, we can say that the region is acceptably homogeneous. If H is between 1 and 2, it's possibly heterogeneous, and if H is greater than 2, it's definitely heterogeneous, and we need to go back and reformulate the region. The homogeneity metric is a measure of how similar the sites are to each other within the region. This is helpful because it produces a single statistic that tells us whether a region has too much variability. The Hosking and Wallace book provides a lot more information about the H statistic and how it's calculated if you wish to learn more. The other statistical test we'll talk about is the discordancy metric. This metric is calculated for each site rather than for each region. The discordancy metric is compared against a critical value. If the discordancy D is above the critical value, then the site is considered to be discordant, and it might not belong in that region. The critical value depends on the number of sites in the region, but is typically on the range of 2 to 3. In the figure to the right, we see a plot of the L-moment ratios L skewness versus LCV. The crosshair in the middle is the region average. When computing the H statistic, the overall homogeneity of the sites in the region are considered. The discordancy metric, on the other hand, is calculated for each site and calculates the distance of the site from the assumed center. The critical value is like these dashed ellipses, which tell us how acceptably far a site can be from the region average. If a site falls outside of this, it is labeled as discordant, which means that the site is more different than the other sites in the region than we expect, and it could mean that the site belongs in a different region. There are a number of other statistics that can be run, such as silhouette width, that we don't have time to cover in this video. Let's talk more about the process to form homogeneous regions. We talked about how sites can be collected into regions using physical measures such as elevation, precipitation, and other variables. When forming the regions, you should try many different combinations of spatial variables and also different combinations of number and size of regions. Once you think you've determined the best combination of spatial variables and size of regions to form your homogeneous regions, the next step is to test their homogeneity. As we discussed previously, the first metric is the homogeneity metric, which is used to check the region homogeneity. Then we can also check the discordancy, which is measured for each site. The figure on the right shows a silhouette plot, which is similar to discordancy. A large negative silhouette width could tell us that this individual site might belong in a different region than the region that is currently assigned to. The goal is to produce regions that all have an acceptable homogeneity metric of less than 2, or even better, less than 1, and have regions that don't have any sites that are discordant. If you do have regions that are not acceptably homogeneous, you can make adjustments. Sometimes it makes sense to merge or split regions if regions have too few or too many sites. It might make sense to move sites from one region to an adjacent region, or you can remove sites entirely. Sometimes this is the case when sites are located on the very edge of our analysis region. Those sites might actually belong in a homogeneous region that we're not even considering in this study. Another adjustment that can be made is to check site data quality. If a site is particularly discordant compared to other sites in the region, it could be pointing to a data quality error. If this is the case, it might make sense to circle back and make sure that the site doesn't have any errors in the data. Discordant sites could also be a result of sites that have a short record length. These just might not have a representative sample of the population and therefore might end up being discordant. This is okay, as we expect some sampling variability in the sites. Once you've made any adjustments to the region that you need to make, then we have to iterate and recheck the homogeneity and discordancy statistics. This is a process that might be repeated multiple times over until you reach a set of regions that are all acceptably homogeneous. Sometimes you might even need to circle back and reevaluate the spatial variables or the size of the regions that you're using to define your regions in the first place. Automated cluster analysis, like you can do in languages such as R and Python, make this process much easier, but it's not a substitute for engineering judgment. Cluster analysis is a great first step to identify subgroupings, but you'll likely have to do some manual adjustments to get your regions to be acceptably homogeneous. In that step, we created homogeneous regions. As Hosking and Wallace said, this is usually the most difficult part of the regional frequency analysis process. The next steps are a little bit easier. We'll first talk about computing L-moment ratios for our regions. Regional L-moment ratios are computed as a weighted average of the sites in the region, weighted by each site's record length. To break down the equation, we have a regional L-moment ratio, and we perform this for each of the ratios LCV, LSKU, and L-kurtosis. That's computed as the sum of the site L-moment ratios, LCV, LSKU, and L-kurtosis, multiplied by the record length of that site. What this does is weight sites that have a long record length more strongly than sites that have a very short record length when determining the overall regional L-moment ratio. This is a very similar mechanism to how regional skew is calculated in streamflow, where regional skew is weighted based on the mean square error, which is inversely related to the site's record length. Once we've computed L-moment ratios, they can be plotted on an L-moment ratio diagram, which we've seen earlier. As a summary for how to use an L-moment ratio diagram, we plot the third L-moment ratio, L-skewness, versus the fourth, L-kurtosis, on the y-axis. These lines on the plot represent common probability distributions. The points that fall in the plot that lie closest to that specific distribution represent the likely best distribution. So for example, for a single region, which in this case is called cluster 1, the black crosses shown here represent the L-skew and L-kurtosis for each site within the region. The blue square, located here, shows the regional average L-skew and L-kurtosis. These data are pretty spread out, which is a result of sampling variability, and the regional average falls somewhere in the middle. And as we stated earlier, we expect the L-moment ratios of sites in a homogeneous region to be reasonably similar. Now the next step, once we've calculated the L-moment ratios, is to identify the appropriate probability distribution, and we can do this again using the L-moment ratio diagram. For this example, for cluster 1, using the regional ratios, which is the blue dot located in the middle, the best distribution would be the generalized extreme value, because this is the distribution that the point falls closest to. When performing regional frequency analysis, the best distribution can also be performed using statistical tests rather than just visually using the LMRD. In the previous slide, we estimated the best probability distribution for a single region. This process would then be repeated for each region. It's important to note that the same distribution doesn't have to be used for all regions within your analysis domain, but it could lead to spatial discontinuities depending on the method of regionalization that's used. This is something that was common in earlier volumes of NOAA Atlas 14. For example, in the table below, different distributions were selected for different regions. You can see what that looks like on the right, where there's a clear boundary between the different regions where different distributions were selected. This isn't a problem for regionalization methods like index flood, where we have to assign a site to a specific region. But it does cause problems for other regionalization methods like mapping, where we need to have a more continuous and smooth boundary. For this reason, a lot of studies will choose to select a single representative distribution for the entire analysis. Finally, we'll talk about estimating parameters. We've collected our data, assigned them to homogeneous regions, computed the L-moment ratios, and determined the best probability distribution, and now we can estimate the probability parameters. This process should sound very similar to the parametric modeling process that was described in earlier lectures. As I mentioned previously, the data collection and creation of homogeneous regions is the biggest difference between this process and typical parametric modeling for at-site analysis. As a quick recap of the index flood method, we use an at-site mean and a regional average, shape, and dispersion. The index flood method computes the site prediction based on a site index flood, which is typically the mean, multiplied by a regional growth curve, which is based on the regional average, standard deviation, and skew. Index flood method is appropriate for a single region or regions that are spatially contiguous. This is because each site needs to be assigned to a distinct region in order to perform index flood. The index flood method is limited in that sites need to be assigned to a specific regional membership, and also adjacent regions can form a sharp boundary because they might have different regional growth curves. One way to overcome this is through mapping, which is another method of regionalization that we talked about earlier. Spatial mapping is a little similar to the index flood in that the variance of regionalization for the mean are determined at site, whereas the LCV and the L-skew are determined based on a regional average value. In spatial mapping, we perform spatial regression or interpolation using the L-mean, LCV, and L-skew. When performing spatial regression, typical covariates such as latitude and longitude, elevation, mean annual precipitation, etc. might be used, as we discussed earlier. So in this example to the left, we have a plot of L-mean for each site within the analysis domain. For L-mean, we are using the at-site values, and we can perform a spatial regression using those at-site values. Next, for LCV and for L-skew, we use the regional average values. We can similarly perform a spatial regression using various spatial covariates and perform the regression using these regional average LCV and L-skew values. What this produces is a spatially continuous map of L-mean, LCV, and L-skew, from which we can estimate for any single point or area, we can grab the L-mean, LCV, and L-skew, even if there's no site located at that location. This is very helpful for estimating locations that don't have a gauge. From the L-mean, LCV, and L-skew, we can fit the probability distribution that we've selected earlier. In this example, we might fit the GEV distribution, which gives us the parameters xi, alpha, and kappa. This is what produces our precipitation frequency curve. Using the generalized extreme value in this example, the parameters xi, alpha, and kappa plot like the curve shown here. This should sound very familiar to the process we followed in the parametric modeling lecture. This frequency curve is also plotted against NOAA Atlas 14 estimates, which is a very common source of precipitation frequency data in the United States. One of the limitations of NOAA Atlas 14 is that it only goes up to the 1 in 1,000 year event. However, NOAA Atlas 14 also performs regional frequency analysis, much like the steps that we've shown here. As you can see, this precipitation frequency curve would provide much more robust estimates of precipitation compared to using a single gauge with a limited period of record. So in summary, regional frequency analysis follows the general steps of determining an analysis domain, collecting data from many gauges, creating homogeneous regions and testing those statistically, For each region, computing regional L moments, and choosing and fitting a probability distribution using the L moment ratio diagram. From there, regionalization methods like the index flood method can be used for sites where you know the mean and you know the region that the site is assigned to. If you need to interpolate to a site where there's no gauge located or where the regions are non-continuous, you should use a method such as mapping, which can interpolate to any point in the domain. This concludes Part 4 of Regional Precipitation Frequency Analysis.